Chapter 9, Part 3, Noise. Distortion is something we've already covered in the course. It's change introduced by circuit components. So, for instance, clipping distortion with an op-amp when the power supply isn't big enough or the gain is too much or the input power is too high. Crossover distortion with a push-pull amplifier when both transistors are trying to conduct in that middle region near the x-axis. And there are other types of distortion as well. Noise is external to the circuit. It's caused by the vibration of atoms. That causes white noise, which if you've got an old TV, it's that kind of fuzz. Electromagnetic interference from other sources, or even from other communication systems. You get a thing called crosstalk, which is why on old telephones you can sometimes get this effect where you actually start to hear someone else's conversation. And that's literally their conversation line crossing over with yours. Now, why is noise such a problem apart from that obvious one? Well, noise has roughly a constant amplitude, and particularly things like white noise, fairly constant. Signal, on the other hand, has a decreasing amplitude due to attenuation. You send it out with a certain amount of power, and as it goes through the atmosphere, it bumps into other atoms and it loses that power slowly over time. So that's the attenuation. And when we combine the two, the problem is our signal loses power and eventually you can't distinguish it from the noise and therefore you can't tell what the original signal was. Let's look at this on a couple of graphs. Now I'll start with a analog graph. So if I add noise, it kind of adds a bit of fuzziness. Now at the moment, at the beginning, that's not really a problem. But as it attenuates, this kind of fuzziness becomes more of a problem. And you can see as we get, sorry, just extend the time axis slightly. This would be voltage. As you get towards here, you can't really tell where your signal is and where your noise is. You can also have the same problem with digital signals. And again, with enough attenuation, that noise will become indistinguishable from the signal. Till eventually, I'm just speeding things up, you can't really tell. So there's a problem. So we need our signal to have a high enough amplitude that we can overcome this noise. And we measure this using the signal to noise ratio. And we measure it in decibels using these two equations. Remember that power is equal to voltage squared over R, and so V squared over R, and if it's inside a log, you can bring the two down in front. That's just a side note for the mathematicians. Do make sure you label this on your data sheet. It is really, really important. How do we estimate it from an actual physical signal? Well, the first thing is we don't actually apply the signal. We measure the ambient background noise without any signal. Well, that's fairly easy to do. And then what we do is we measure the noise and the signal together. And to work out the signal on its own, we simply do the signal and noise, take away the noise. Then we plug in the equation. Let's have a look at some questions. So here are 3 questions. I would recommend that you pause the video at this point and have a go at these 3 questions yourself before I go on. And try and do it just with the equation written in front of you and not with all the notes. Okay, question 1. We have been given the signal and the noise voltages, and we're asked to estimate the signal to noise ratio. It's estimate because the other values are estimates. So we stick this in the equation that we've got. It's voltages, so it's the one with 20 in it. So that's going to be 150 times 10 to the minus 3 over 215 times 10 to the minus 6. Units are really, really important. Don't forget your units, otherwise you're talking gibberish. And we stick that in a calculator to get a signal to noise ratio of 56.9 decibels. Nice and easy, 1 mark question. Stick numbers in a formula. Okay, question 2, a little bit more tricky this time because we have got to do a little bit of rearranging. This is where you've got to be comfortable flipping in and out of log form. So we've got the input signal, we've got the signal to noise ratio, and we need to work out the maximum acceptable noise path. So 20 decibels is equal to, this one's 10 because we're talking about power. We've got the input, so that's the signal, so that's 2 watts. And we want to work out the power of the noise that is acceptable. So you do it divide by 10. And we take it out of log form. We multiply by the noise power. And we divide by 10 to the 2, which is of course 100. And we put that on a calculator. You probably could see that that's just 0.02 watts or 20 milliwatts. So that's the second question. This is often the step that students find tricky, particularly those who aren't doing A-level maths. So just make sure you're comfortable with it. Okay, question 3. The amplitude of the noise is 8 millivolts. We've got the signal to noise ratio. This time we're trying to work out the voltage of the signal. So again, stick in the equation, rearrange, solve. Voltages, so it's going to be a 20 this time at the front. Do you remember that there are different numbers, and that does often trip students up. Divide by 20. You don't need to write the 10. The textbook does and the exam sheet does, but if you don't write it, people assume that you mean 10. Multiply by 8. It's in millivolts, don't forget. It's always useful to write your units as you go through so you don't forget them. And that gives you that the signal voltage is 318 millivolts. And obviously it's a lot higher, but that's what you expect. You expect it to be a lot higher. Okay, question 4 is significantly more tricky. I would recommend again that you pause the video and have a go at the question. But don't worry if you get it wrong, this one is more tricky. You could well get a question like this on the exam, so do make sure you're comfortable and you understand it, even if you get it wrong the first time. Okay, so we've been given the noise power, so this is noise, and this is noise and signal. So we want to work out the signal, we do the noise and signal minus the noise. So 57 milliwatts minus 150 microwatts. Don't forget your units, otherwise it's gibberish. I'm just being a bit slow putting numbers in a calculator. Sorry about that. It's 56.85 milliwatts. So you make sure, again, you're really careful with your units. And then just put it in the signal to noise ratio. And we've got power, so it's going to be the one with 10 at the front. So that is 25.8 decibels. Okay, right, we're told in the next question the cable is 12 kilometers long and has attenuation of 3.7 decibels per kilometer. So to work out the total attenuation, we just multiply the two. Let's start by doing that. That's probably going to be useful, isn't it? So that's 44.4 decibels. Remember, because it's attenuation, it's decreasing, it's a negative value for the decibels, not a positive one. So just something to watch out for. And we're asked to calculate the minimum input power of the signal to achieve the signal to noise ratio calculated above without any kind of amplification. So this brings us back to the equation we looked at in the previous part, which is the gain is equal to the output power over the input power. We know what the gain is, it's minus 44.4. We know what the output power is because that was this value up here. This is the output power. If we had any lower value, we'd end up with a lower signal to noise ratio. We just need to work out the input power. So again, a bit of rearranging, etc. So divide by 10 minus 4.44 log, and then the stuff in the bracket hasn't changed. And then taking it out of log form, 10 to the minus 4.44 is equal to 56.85 milliwatts over the input power. Now I'm going to swap these two over. I can do because I multiplied by the input power and divide by 10 to the minus 4.44. And put that in a calculator. And the input power has to be rather large to keep this value. Which is probably because I made up silly numbers. 1,566 watts, which is obviously ridiculously big. In the exam, you would expect slightly nicer numbers. That's because the attenuation is actually pretty high, and we still want quite a high output wattage. Okay, last thing to cover, what to do about noise. For an analog signal, we can't get rid of noise. There's no way you can kind of really get rid of it because it's all the analog signal can take any value, so we don't know if that's noise or just a normal signal. So what we can do is add repeaters. So these are things that have a low amount of noise, but they have a high amount of amplification, usually power amplifiers. So what we do is we use those, they add minimum amount of noise and they increase the amplitude of the whole wave. So that increases the signal amount and doesn't have such a big impact on the noise, because when you multiply a small number by a large amplification, it doesn't really increase much. So that's what we do with analog signals. Digital signals are much better actually, because we can make them fully digital again by using a Schmitt trigger. Remember, a Schmitt trigger output is always digital. It's always saturating either high or low. So digital signals are much better for dealing with noise. And that's often why we will convert analog signals into digital signals, because it's easier to then send them over large distances without having to spend lots of money on lots of amplifiers and lots of repeaters sort of thing. And that's it. That's noise. Do you make sure you got the notes on all this? Do you make sure you've written down the notes on all the examples? And all of this communications chapter will come up when we look at wireless communication, digital communication, and optical communication. So make sure that you are really happy with all of this stuff before Christmas, because after Christmas, in that first half term back, we're going to be looking at all those bits. Have a nice Christmas.